Welcome to this new video presentation on oscillations part 2. This is continuation of our previous video, that is oscillations part 1. In part 1 we studied about periodic and oscillatory motions, simple harmonic motion and uniform circular motion, velocity and acceleration in SHM, and force law for simple harmonic motion. Today we will continue our discussions with energy in SHM, some systems executing simple harmonic motion, damped simple harmonic motion, forced oscillation and resonance. Finally, we will end today's session by answering questions of 1 and 2 marks, as well as we will take up some long answer type of questions. I welcome you once again. Please note down all the important points. Energy in simple harmonic motion. In the previous section, we have seen that the velocity of a particle executing simple harmonic motion is a periodic function of time. Both kinetic energy and potential energy of a particle in simple harmonic motion vary between 0 and their maximum values. The velocity of a particle in periodic function of time, hence it is 0 at the extreme position of displacement. That is, if the displacement is maximum, velocity is 0. The kinetic energy represented by the letter capital K of such a particle in simple harmonic motion is defined as capital K is equal to half into m into v square. Here capital K is the kinetic energy, m is the mass of the particle and v is the velocity of the particle. We know that the value of v, velocity in simple harmonic motion, is represented by omega a into sine omega t plus phi. Hence, the previous equation k is equal to half mv square becomes capital K is equal to half into m into omega square a square sine square omega t plus phi. Now we can put the value of m into omega square as a small k. That is another constant called the spring constant. So capital K, the kinetic energy, can be written as half into small k into a square into sine square omega t plus phi. Let it be equation 1. Here in this equation, please recall that capital A is the amplitude, omega is the angular frequency and phi is the phase constant. Let it be equation 1. If we plot equation 1, that is kinetic energy versus the time on the x-axis and the kinetic energy and the y-axis, we get the graph as shown in the figure. Here, please note the kinetic energy is also periodic with a repetition at t by 2. Period time period is t by 2, representing all halfways. Hence, kinetic energy is also a periodic function, being 0 when the displacement is maximum. So at this point 1, 2, 3, displacement is maximum, but kinetic energy is 0. And kinetic energy is maximum at the mean position. So this is a mean position and it is the kinetic energy is maximum. Since the sign of V is immaterial in kinetic energy, the period of kinetic energy is T by 2 as shown in the graph on the screen. Next we will take up potential energy U. The concept of potential energy is possible due to law of conservation of force. We also know that the spring force F is also a conservative force, and it is represented by the letter capital F is equal to minus small k into x, which is a conservative force, and its associated potential energy represented by capital U of x is equal to half k into x square, small k x square. Let it be equation 2. But we know that displacement is represented by A into cos omega t plus phi. Hence, putting x as A cos omega t plus phi, we get potential energy U of x is equal to half of k small k into A square cos square omega t plus phi. Here small k is the spring constant, A is the amplitude, and omega is the angular velocity, and phi is the phase constant. Let it be equation 3. The plot of equation 3 versus time is shown in the graph 2 on the screen. Here in the x-axis we are plotting the time t, and on the y-axis it is potential energy. Hence, we observe that the potential energy is also a periodic function. Is periodic, and it is given by the letter u is equal to half into small k into x square as shown in equation 2. Thus, the potential energy of a particle executing simple harmonic motion is also periodic with period t by 2. You see here in the graph 2 also the period is t by 2, being 0 at the mean position. So, potential energy is 0 at the mean position and maximum at the extreme displacement. That is, when the displacement is maximum, potential energy is also maximum. Potential energy is 0 at the mean position. It follows from equation 1, 2 and 3 that total energy is given by potential energy plus kinetic energy. Substituting the values of U and K from equation 1 and 3, we get E is equal to half of K A square into cos square omega t plus phi plus half M into omega square A square into sin square omega t plus phi. These equations are plotted here. Here you see the inverted cup is a kinetic energy. The graph inverted cup is a kinetic energy, and the cup shape is potential energy. When we add up potential energy and kinetic energy, we get the value of total energy, which is a flat line parallel to the x-axis. Here energy is on y-axis and time is on the x-axis. Therefore, these equations can be represented taking Ka square common. We get half of Ka square into cos square omega t plus phi plus sin square omega t plus phi. We know that cos square A plus sin square A is 1. Therefore, this equation, the value of the trigonometric function in the big bracket is 1. Therefore, the total energy will be is equal to half of Ka square. Let it be equation 4. The simplest example of system executing simple harmonic motion is oscillations due to a spring. Please consider a block of mass m fixed to a spring, which in turn is fixed to a rigid wall as shown in the figure. The block is placed on a frictionless horizontal surface. If the block is pulled on one side and is released, then it executes to and fro motion about its mean position. Let x is equal to 0, that is x is equal to 0 as shown in the figure, indicates the position of the center of block when spring is in equilibrium. The positions marked as minus A on the left hand side and plus A on the right hand side indicate the maximum displacements to the left and right of the mean position. Springs have special properties that such a system when displaced is subject to a restoring forces. Spring has got a restoring force. The magnitude of this restoring force is proportional to the displacement and acts in the opposite direction. Suppose you pull the block on the right hand side, the spring force acts on the left hand side. This is known as Hooke's law, which we have studied in our previous sections. It holds good for displacements small in comparison to the length of the spring. Please note the displacements in case of oscillations due to a spring should be very small as compared to the length of the spring. At any time t, if the displacement of the block from its mean position is x, the restoring force F acting on the block is given by the relations f of x is equal to minus k into x. Let it be equation 1. In this equation, F is a force and k is the constant of proportionality called the spring constant, whose value depends on the properties of the spring. The spring can be tough or a soft also. So the value of k depends on the elastic properties of the spring. X is of course the displacement. Let it be equation 1. A stiff spring has a large value of k and a soft spring has a small value of k. Equation 1 is same as the force law for simple harmonic motion and therefore the system executes a simple harmonic motion. The angular frequency is given by the angular frequency of the spring is given by the relations omega is equal to square root of k small k by m, where omega is the angular frequency, small k is the spring constant and m is the weight of the block as shown in the figure. And also the period of oscillator is given by the relations capital T is equal to 2 pi into square root of m by k. This relationship we have proved it in our previous video lesson. Second example of system executing simple harmonic motion is a simple pendulum. Please see the figure which shows the a bob oscillating about its mean position. Consider a pendulum, a small bob of M tied to the inextendable massless string. This bob is tied to a string of length capital L, but it cannot be this length of string is not extendable and its length L remains constant. The other end of the string is fixed to a rigid support here on the top. The bob oscillates in the plane about the vertical line through the support. So the bob oscillates left to right or right to left and moves about its to and fro between its mean position. This figure shows the free body diagram of a simple pendulum showing the forces acting on the bob. Let theta be the angle. This is the theta angle made by the string with vertical. When the bob is at the mean position, that is at the center here, theta equal to 0. When the bob is at the center, theta equals 0. There are only two forces acting on the bob. The tension T, which is along the length of the string, and vertical force due to mg. This is vertical force due to the mass mg, it is acting downward, where m is the mass and G is the acceleration due to gravity. The force mg can be resolved into two components, mg cos theta, see here by the geometry of the figure, mg cos theta and mg sin theta, that is perpendicular to the length of the string. Since the motion of the bob is along the circle of the length L and center of the support of the point, the bob has a radial acceleration omega square into L and also a tangential acceleration. The latter arises since the motion along the arc of the circle, this is the arc of the circle, is not uniform. The radial acceleration is provided by the net radial force T minus mg cos theta. See, T acts here and mg cos theta is downward. So net force is T minus mg cos theta, while the tangent force is given provided by mg sin theta. This is mg sin theta, this is tangential force, and this is the radial force. Now it is easier to calculate the forces and analyze in terms of torque. Therefore, torque tau about the support is entirely provided by the tangential force, that is mg sin theta. Therefore, tau is equal to minus of L into mg sin theta. This is restoring torque that tends to reduce the angular displacement, hence the negative signs. This is the restoring torque, and this negative sign in equation 1 is due to the restoring force. By Newton's law of rotational motion, we know that tau is equal to I into alpha, where I is the moment of inertia and alpha is the angular acceleration. Therefore, it is the moment of inertia and alpha is the angular acceleration, and tau is the tangential component of the force. Therefore, I alpha is equal to minus mg sin theta into L, that is equating equation 2 and 1, and eliminating tau, we get I into alpha is equal to minus mg into sin theta into L. That is, or we can state that alpha, the angular acceleration, is given by alpha is equal to mg capital L divided by I into sin theta. Let it be equation 3. For smaller values of theta, sin theta is approximately equal to theta. Therefore, we can write alpha, equation 3, as alpha is equal to mgl divided by I into theta, because sin theta is approximately equal to theta for smaller values of theta. Let it be equation 4. Hence, it is proved that smaller values of theta, the motion of bob is simple harmonic, and omega is equal to square root of mgl divided by I, and tau is equal to 2 pi into square root of I divided by m into gl. Let it be equation 5. Since the string of the simple pendulum is massless, I is equal to m into L square. That is, where I is the moment of inertia, m is the mass, and L is the length of the string. So therefore, equation 5 becomes T is equal to 2 pi into I divided by G. Let it be equation 6. Damped simple harmonic motion. Consider a system having a block of mass m connected to an elastic spring constant spring constant small k, which oscillates vertically as shown in figure. So this is a block, attached to a spring which is fixed on the top support, rigid support. So the movement of this block is vertically up and down. If the block is pushed downwards and released, its angular frequency is given by the relation omega is equal to square root of small k by m, where omega is the angular velocity of the spring and small k is the spring constant and m is the mass of the bob or the block, mass of the block. The surrounding medium here, which may be a fluid or viscous or any other medium, offers a damping force on the motion of the block. That is, the surrounding viscosity, liquid or anything will restrict a damping force to the block. So this surrounding medium is shown in the figure as dotted particles. And the mechanical energy of the block spring will decrease because the surrounding medium offers resistance, and the mechanical energy decreases due to loss of energy, which will appear as heat. Sometimes that will appear as the heat. The damping force, represented by the letter capital F subscript D, is proportional to the velocity of the bob or the block, velocity of the block. That is as per Stokes' law. Therefore, Fd, which is a vector, equals minus b into v, vector v. That is for small velocities where the positive constant v depends on the characteristics of the medium and the size and shape of the block. So this constant b is due to the medium, surrounding medium and size and shape of the block. Hence Fd is equal to minus b into v, vector. So both Fd and velocity are vector. Let it be equation 1. If the mass is pulled down or pushed up little, the restoring force on the block due to spring is given by Fs. This is F subscript S is a restoring force, equal to minus k into x, where k is the spring constant and x is the displacement. Thus, the force acting on the mass at any time t is given by F is equal to the sum of Fs plus Fd, that is equal to minus kx minus b into v. So if a is the acceleration of the mass at time t, then by Newton's law of motion applied along the direction of motion, we have m into a. Force is m into a equals minus kx minus bv, which is a function of time. Let it be equation 2. So this force acts as a damping force. A damped oscillator is approximately periodic with decreasing. Please see the graph here. The amplitude is decreasing with oscillation with respect to time. Time t is an x-axis and amplitude or displacement is on the y-axis. So plus a is here on the top, minus a at the bottom. So this it increases, and as the resistance from the medium and the restoring increases, then the oscillations decrease. It is called a damped oscillator, which is approximately periodic with decreasing amplitude of oscillation. With greater damping, oscillations die out faster. If the damping force is more, these oscillations die out faster. Using the first and second derivatives of x of t and velocity and acceleration, which we have derived in our previous video, whose description is given in the link, we can write this equation as m into ax square, that is m into d squared x by dt square. D squared x by dt square is acceleration, plus b of dx by dt. This is the velocity. Dx by dt is the velocity, plus kx is equal to 0. This is the differential equation. Let it be equation 3. This solution, if we find the solution for this equation number 3, we get x of t as a to the power of a into e to the power of minus b into t by 2m into cos omega dash t plus phi. This solution you have to remember. This derivation is beyond the scope of this lesson. Let it be equation 4, where here in this equation 4, a is the amplitude and omega dash is the angular frequency of the damped oscillator, given by the relation omega dash is equal to, that is considering the damped simple harmonic motion, omega dash is equal to square root of k by m minus b square by 4m square. The k, b and m are as stated earlier. Let it be equation 5. Here it is very important to note the mechanical energy of the damped simple harmonic motion. For small values of damping, we know that b divided by square root of k by m. Square root of k by m is very small. Therefore, energy which is given by the relation E is equal to k a square becomes E of t is equal to half of k into a square into e to the power of minus b into t by 2m. This is the damping constant. Hence, the total energy also decreases exponentially with time, because this function is an exponential function with decreasing values. Forced oscillations and resonance. When a system is displaced from its equilibrium position and release, it oscillates with its natural frequency omega, and the oscillations are called free oscillations. But these free oscillations die out because of damping forces. However, in order to maintain these oscillations, we had to apply an external force. Under such conditions, it is called forced or driven oscillations. Thus, the oscillation in which a body oscillates under the influence of an external periodic force are known as forced oscillations. Suppose an external force F of t is applied to a damped oscillation, and the force is given by the relation f of t is equal to f naught into cos omega dt, where omega d is the driving angular frequency and f of t is the force, f naught is the amplitude. The motion of a particle is the combination of three forces. One is linear forces minus x of t, and damping force minus b into v of t, and plus the external force F naught cos omega dt. Let it be equation 2a. Substituting and rearranging in terms of differential equation, we can retain the last term on the right hand side. The remaining terms can be expressed as m of d squared x by dt squared plus b of dx by dt plus k into x, because we have just put the values of acceleration, displacement and the velocity. Let it be equation 2b. This is the equation of oscillator of mass m, which is with a periodic force of frequency omega d. The oscillator initially oscillates with natural frequency omega, and when we apply external force, the oscillations, that is with natural frequency, die out, and then the body oscillates with only external periodic force. Its displacement after natural oscillation is given by the relation x of t is equal to a into cos of omega d into t plus phi. Let it be equation 3. Here the value of a is written as, a can be written as a is equal to f naught over square root of m square into omega square d square, omega square minus d square whole square plus omega d square b square. Let it be equation 4a, and its phase constant is given by the relation tan of phi is equal to minus v naught by omega d into x naught. Let it be equation 4b. When where m is the mass of particle, v naught and x naught are the velocity and displacement of the particle at a time t equal to 0, when we actually apply the periodic force, external force. These can be plotted in a graph shown on the screen. In the x-axis, we have plotted the ratio omega d by omega, where omega d is the driving angular velocity, omega is the natural frequency, angular frequency, and amplitude is plotted on the y-axis. So there are three curves for different values of b, that is a damping constant b. The amplitude is greatest when omega d by omega is ratio is 1, that is omega d is equal to omega. So at this position, resonance is said to have occurred. The three curves correspond to different extents of damping present in the system. The curves 1 and 3 correspond to the minimum and maximum damping in the system. You please note here, for curve 1, the damping is minimum, least damping, and for curve 3, damping is maximum. So these conditions are written once again in the insert box. So that is, when omega d into b is far less than m into omega square minus omega d square, then a is given by f naught is equal to m into omega square into minus omega d square. That is, you substitute, reject the value of omega d into b. If you reject this, you will get this value. But in the second case, when omega d is approximately equal to omega, we will get, that is, omega d into b is far greater than m into omega square minus omega d square. A is equal to, amplitude is equal to f naught by omega d into b. This is plotted in the graph. Thus, resonance is when the frequency of external force is equal to the natural frequency of the oscillator, then this state is known as the state of resonance, and this frequency is known as resonant frequency. Now we will answer very short questions of 1 mark. Question number 1. How is the time period affected if the amplitude of a simple pendulum is increased? There is no effect, as the time period is independent of the amplitude. Define force constant. We know that F is equal to minus K into X. Therefore, K is equal to minus of F by X, that is force by displacement. Question 3. At what distance the mean position is the kinetic energy in simple harmonic motion oscillator equal to the potential energy? At x is equal to a by root 2, that is, kinetic energy equals potential energy is equal to 1/4 of m into omega square a square. How is the frequency of oscillation related with frequency of change in kinetic energy and potential energy of the body in simple harmonic motion? Potential energy or kinetic energy completes two vibrations in a time during which simple harmonic motion completes one vibration. That is, if simple harmonic motion completes one vibration, then potential energy or kinetic energy complete two vibrations. Or the frequency of potential energy or kinetic energy is double than the simple harmonic motion. What is the frequency of the total energy of a particle in simple harmonic motion? The frequency of total energy of the particle in SHM simple harmonic motion is zero because it remains constant. You remember the curve of potential energy, kinetic energy and total energy. Total energy is a flat line, hence it remains constant. How is the length of seconds pendulum related with the acceleration due to gravity of any planet? Length of seconds pendulum is proportional to the acceleration due to gravity. Please remember the formula. Question number 7. The bob of a simple pendulum is made to oscillate in some fluid of density greater than the density of air. That is, density of bob is greater than the density of fluid. Then time period of pendulum is increases or decreases. It is increased. Question 8. How is the time period of pendulum affected when the pendulum is taken to hills or in mines? Answer. We know that T is proportional to 1 over square root of G. T, therefore the period will increase. Define the angular frequency. Give its SI unit. Angular frequency is the angle covered per unit time, or it is the quantity obtained by multiplying frequency by a factor 2 pi. That is, we can write omega is equal to 2 pi f, where f is the frequency, linear frequency. SI unit is radians per second. Question number 10. Does the direction of acceleration at various points due to oscillation of a simple pendulum remain towards the mean position? No. The resultant of the tension in the string and the weight of the bob is not always towards the mean position. Question number 11. What is the time period of function ft is equal to sin omega t plus cos omega t? May represent the simple harmonic motion. Therefore, if the value of t is equal to 2 pi by omega, then it represents the simple harmonic motion. Next question. When is the swinging of a simple pendulum considered approximately simple harmonic motion? That is, when swinging through small angle. That is, sin theta is approximately equal to theta. That is small angle. Next question. Can the motion of an artificial satellite around the Earth be taken as simple harmonic motion? Answer. No. It is a uniform circular motion, but not simple harmonic motion. What is the phase relationship between displacement velocity and acceleration in simple harmonic motion? In simple harmonic motion, the velocity leads the displacement by a phase angle pi by 2, that is 90 degrees, pi by 2 radians, and acceleration leads the velocity by a phase of pi by 2 radians. So phase relationship and simple, this we have proved it. What force keeps the simple pendulum in motion? The component of the weight mg sin theta. How will the time period of simple pendulum change when its length is doubled? When it is doubled, that is it changes by root 2 times as t is proportional to square root of L, where L is the length of pendulum. Next question. If the motion of revolving particle is periodic in nature, give the nature of motion or projection of the revolving particle along the diameter. So the motion is simple harmonic motion. Question number 18. In a forced oscillation of a particle, the amplitude is maximum for frequency omega 1 of the force, while the energy is maximum for omega 2. What is the relation between omega 1 and omega 2? Answer. Both amplitude and energy of particle can be maximum only in the case of resonance. For resonance, the relationship is omega 1 equals omega 2. When will the motion of simple pendulum be simple harmonic? When the displacement of bob from the mean position is so small that sin theta is approximately equal to theta. Question number 20. A simple harmonic motion of acceleration A and displacement x is represented by the equation A plus 4 pi squared x equal to 0. What is the time period of simple harmonic motion? A is equal to, rearranging this equation, given equation, A is equal to minus 4 pi square x. Or we also know that acceleration is given by minus omega squared x. This is A is minus omega squared. Therefore, omega is equal to, equating these two, cancelling x, omega is equal to 2 pi. Therefore, t is equal to 2 pi by omega, or 2 pi by omega is 2 pi. Substituting the value of omega, 2 pi gets cancelled. Therefore, time period is 1 second. You please practice this relation. Simple formula. Question number 21. What is the main difference between forced oscillations and resonance? The frequency of external force is different from the natural frequency of oscillator in case of forced oscillation. But in the resonance, two frequencies are equal. Please note, in resonance, two frequencies are equal. Define amplitude of simple harmonic motion. See, amplitude is the maximum displacement of oscillating particle on either side of its mean position. What is the condition to be satisfied by a mathematical relation between time and displacement to describe a periodic motion? So the mathematical relation is y of t is equal to y of t plus t, where capital T is the period and small t is the instantaneous time. It can be y of t plus t is equal to y of t plus 2t, etc., etc. That is, it repeats. Short questions of 2 marks. Question number 24. Which of the following condition is not sufficient for simple harmonic motion and why? Here, two questions are given, conditions are given. One condition is acceleration and displacement, and second one is restoring force and displacement. We have to identify the insufficient condition for describing the physical quantities. Answer is condition 1 is insufficient. That is, it is not sufficient because direction of acceleration is not mentioned. In simple harmonic motion, the acceleration is always in the direction opposite to that of the displacement. Question number 25. The formula for time period t for a loaded spring is given by capital T is equal to 2 pi into square root of displacement or acceleration. The question is, does the time period depend on the length of the spring? Answer. Although the length is not mentioned in the expression, given expression, But the time period depends on the length of the spring. It is because force constant of the spring depends on the length of the spring. Question number 26. Time period of a particle in simple harmonic motion depends on the force constant K and mass m. According to the equation, T is equal to 2 pi into square root of m by k. A simple pendulum for small angular displacement executes simple harmonic motion approximately. Why then is the time period of pendulum independent of the mass of the pendulum? So the question here is, the time period of the particle in simple harmonic motion depends on T is equal to 2 pi into square root of m by k. Then the question is, why the time period of pendulum is independent of the mass of the pendulum? This is a very ticklish question. The restoring force in case of simple pendulum is given by F is equal to mg by L into Y. Here K is equal to mg by L in this equation. Therefore, the force constant itself is proportional to mass, as the value of K is substituted in the formula. M gets cancelled. Question number 27. What is the frequency of oscillation of a simple pendulum mounted in a cabin that is falling freely? Falling freely means G is equal to 0. Answer. The pendulum is in a state of weightlessness, that is G equals 0. The frequency of pendulum F is equal to 1 over 2 pi into square root of G by L. Since G is 0, the frequency is also equal to 0. Next question. The maximum acceleration of simple harmonic oscillator is A0, while maximum velocity is V0. Calculate the amplitude of the motion. Answer. A max is equal to, we know that A max is equal to omega square A. That is given as A0. So therefore, small a acceleration is equal to A0 by omega square, equating these two, the second and the third terms. Therefore, the u max, that is initial displacement, when the velocity is initial velocity, maximum velocity is omega into a, that is equal to given as v0. Therefore, omega is equal to v0 by a. Therefore, it implies that a is equal to a0 by omega v0 square by a square, that is substituting omega equals v0 by a in this equation, the first equation, say. Therefore, a is equal to v0 square by a0. Therefore, the value of a0 is v0 square by small a, acceleration. Question number 29. The displacement of particle in simple harmonic motion is given by the relation y is equal to a sin omega t plus phi. Show that the time t is increased by 2 pi by omega, the value of the y remains same. That is, if the small t is increased by 2 pi by omega, the value of y remains same. So the displacement at any time is given by y is equal to a sin omega t plus phi. Displacement at any time is equal to t plus 2 pi by omega will be given by the relation. So that is, the period is 2 pi by omega. Therefore, y is equal to a sin into omega into t plus 2 pi omega plus phi. That is again repeated after second period. That is sin omega t plus phi plus 2 pi. Therefore, that y is equal to sin omega t plus phi, because sin of 2 pi plus phi is equal to sin phi itself. Hence, displacement at time t and t plus 2 pi by omega are same. Now we will take up long answer questions. So the time is very short. We will just review it quickly. On average, the human heart is found to beat 75 times in a minute. Calculate its frequency and period. The beat frequency of heart is 75 divided by 1 minute. That is equal to 75 by 60 seconds. Converting minute into seconds. That is equal to 1.25 per second. Therefore, that is 1.25 hertz. The time period is given by capital T is equal to 1 over 1.25 per second. Therefore, that is equal to 0.8 seconds. Question number 2. Which of the following functions of the time represent a periodic and non-periodic motion? Give the period for each of the periodic motion. Omega is any positive constant. Sin omega t plus cos omega t. Answer. The sin omega t plus cos omega t is a periodic function. It can also be written as square root of 2 into sin omega t plus pi by 4. Now square root of 2 sin omega t plus pi by 4 is equal to root 2 into sin omega t plus pi by 4 plus 2 pi. So that becomes root 2 into sin omega of t plus 2 pi by omega plus pi by 4. Because it is periodic. So the periodic time of function is 2 pi by omega. Next part is sin omega t plus sin omega t plus cos 2 omega t plus sin 4 omega t. Therefore, this is an example of periodic motion. It can be noted that each term represents a periodic function with a different angular frequency. Since the period is the least interval of time after which the function repeats itself, sin omega t has a period t naught is equal to 2 pi by omega. Therefore, cos 2 omega t has a period pi by omega, that is t naught by 2. Sin omega t has a period of 2 pi divided, sin 4 omega t has a period of 2 pi by 4 omega, that is equal to t naught by 4. The period of the first term is a multiple periods of the last two terms. Therefore, the smallest interval time after which the sum of the three terms repeats is t naught, and thus the sum is periodic function with a period 2 pi by omega. The third part is e to the power of minus omega t. This is an exponential function and is not a periodic. Log of omega t. So log of omega t, the function log omega t increases monotonically with time. It therefore never represents its value and is a non-periodic function. It may be noted that as t tends to infinity, log omega t diverges to infinity. It is therefore cannot represent any kind of physical displacement. Next question. Which of the following functions of time represent simple harmonic motion? And part B, periodic but not simple harmonic. Give the period for each. Cos omega t minus sin omega t. Answer. Sin omega t minus sin of pi by 2 minus omega t. That is, you have to remember all trigonometric relations to solve the problems on simple harmonic motion. Please repeat and refresh your knowledge of trigonometry. Therefore, the given equation cos omega t is sin pi by 2 minus omega t. Therefore, it is 2 into cos pi by 4 into sin omega t minus pi by 4. That is equal to root 2 sin omega t minus pi by 4. This function represents a simple harmonic motion having a period capital T is equal to 2 pi by omega and phase angle is minus pi by 4 or 7 pi by 4. This is 7 pi by 4. It comes in the fourth quadrant. That is minus pi by 4. Next part is sin squared omega t. Sin square omega t can be written as half minus half into cos 2 omega t. So the period, this is a periodic function having a period t is equal to capital T is equal to pi by omega. It also represents a harmonic motion with the point of equilibrium occurring at half instead of 0. Question number 4. A body oscillates with SHM according to the equation x is equal to 5 cos of 2 pi t plus pi by 4. At t is equal to 1.5 second, calculate the displacement, speed and acceleration of the body. The angular frequency omega equals 2 pi per second and its time period is t is equal to 1 second. At t is equal to 1.5 second, substituting the value, displacement x is equal to 5 meter into 2 pi into per second into 1.5. The value of t is 1.5 second plus pi by 4. Simplifying, we get the answer as minus 3.535 meters. Now, to solve the part B, we will apply the formula V of t is equal to, that is differential of a omega into sin omega t plus pi by 2. The speed is given by, and now we can put the values of constant, minus 5 meters into 2 pi per second into sine of 2 pi per second into 1.5 plus pi by 4. Simplifying, we get the answer as 22 milliseconds meters per second. For part C, acceleration Vt is equal to dx by dt. So acceleration is, now if we put the dx by dt, it is minus 2 pi per second whole square into displacement. That becomes, simplifying, 140 meters per second. Next question. The figure below shows two circular motions. The radius of the circle, the period of revolution and initial position of the sense of revolution are given in the figure. Please note down the figure very carefully and particularly the parameters given. Obtain the simple harmonic motion of the x projection of the radius vector of the particle P in each case. That is, particle P is rotating in anticlockwise direction in figure A, and in the case of B, it is rotating in the clockwise motion. So the different parameters are given. Let us solve the problem quickly. At t equal to 0 in this figure A, OP makes an angle of 45 degrees as given in the figure with positive x-axis. And after time t, the angle is 2 pi by t, capital T into t in the anti-clockwise direction sense, and makes an angle of pi by 4 plus 2 pi by t, capital T into t with x-axis. The projection of OP is given by the relation x of t is equal to a into, where a is the radius, cos of 2 pi by t plus pi by 4. Therefore, in this case, put t is equal to 4 because it is given in the diagram. So, putting t is equal to 4 and solving, we get the equation of x of t is a cos of 2 pi by 4 plus pi by 4. So, it is a simple harmonic motion with period 4 seconds and initial phase is pi by 4. Part B, that is for a bigger circle B. In this case, at t is equal to 0, OP makes an angle 90, that is pi by 2. And after time t, it makes 2 pi by t, capital T, in clockwise direction, and makes an angle pi by 2 minus 2 pi by t into t with x-axis. The projection of OP on x-axis at a given time is given by the relation x of t is equal to b cos of pi by 2 minus 2 pi by t, capital T into t, that is equal to b of sine 2 pi by t. So here cos is changed to sine because of the 90 degree pi by 2 function, trigonometric ratios. If you put the value of t is equal to 30 in this equation, we get the equation for displacement as x of t is equal to a cos omega t by phi, and why we find that it represents simple harmonic motion of amplitude b and period 30 seconds and initial phase of minus pi by 2. Two identical springs of spring constant K are attached to a block of mass M and fixed supports as shown in the figure below. Show that when the mass is displaced from its equilibrium position on either side, it executes a simple harmonic motion. Find the period of oscillation. Let us answer it. Let the mass be displaced by a small distance x to the right side of the equilibrium position as shown in the figure. So, first consider the displacement towards the right side. In such a situation, the spring on the left side gets elongated and by a length equal to x, and on the right side gets compressed by the same length. This spring gets compressed and this spring on the left side gets elongated. The forces acting on them are F1 is equal to minus K into X and F2 is equal to minus K into X, force exerted by the spring on the right side as well as the left side. Therefore, the net force is given by F is equal to summing up minus 2K into X. Hence, the force acting on the mass is proportional to the displacement and is directed towards the mean position. Therefore, the motion executed by the mass is simple harmonic and its time period is given by the relation capital T is equal to 2 pi into square root of m by 2k. Here the force is 2k. This spring constant is 2k. A 5 kg collar is attached to a spring of constant K is equal to 500 newtons per meter. It slides without friction over a horizontal rod. The collar is displaced from its equilibrium position by 10 centimeters and released. Calculate period of oscillation, maximum speed and maximum acceleration of the collar. Let us answer it. Please read the question once or twice and note down all the given parameters. The period of oscillation is given by the relation capital T is equal to 2 pi into square root of m by small k, where all the notations are standard notations. So substituting the given values, we get capital T is equal to 0.63 seconds. So the velocity is given by the relation omega t is equal to minus a into omega sine of omega t plus phi, where all the notations are using standard symbols. Therefore, V maximum, that is maximum speed, is given by a into omega, that is equal to a is 0.1 into square root of k by m, that is equal to 0.1 into substituting the values, and it occurs at 1 meter, that is velocity maximum is 1 meter per second, and it occurs at x is equal to 0. The acceleration of the collar is given by the relation a of t is equal to omega square into x of t. So that is also given by omega value is square root of k by m, that is equal to minus k by m into x of t. So substituting the values, the a maximum is omega square into a, and that is the values substituting the value of k and m and a displacement of 0.1 meter, that is 1 centimeter, we get it as 10 meters per second square, and it occurs at the extremities. Next question, what is the length of a simple pendulum which takes 2 seconds? So at the time period of simple pendulum is given by t is equal to 2 pi into square root of L by G, where L is the length of the string. Therefore, capital L is equal to GT square, simplifying GT square and 4 pi square. That is, you're taking square. T square is equal to 2 pi square is 4 pi square. It is L by G. Therefore, time period of simple pendulum which takes 2 seconds is Therefore, G is equal to 9.8 meters per second and T is equal to 2 seconds, given values, and L is equal to, substituting, we get length is equal to 1 meter. Here G, we have to remember that it is 9.8 meters per second and T is equal to 2 seconds, you have to remember. With this, we conclude the chapter on oscillation. Next, we will take up our discussions on chapter number 50, new chapter, waves. Till then, goodbye.